Hey guys, in this video we are gonna go through filtration method. So basically we're gonna go through normal and tangential flow filtration, operation, installation, scale up, process development, and tangential flow filtration. Uh, in an interview, a lot of people ask about process development. So you can say that um, you have done some work in process development. We're gonna go through process development. There are two types of process development: constant pressure and constant volume. So we're gonna go through both of them. Where they're exactly used, and also scale up is pretty important. A lot of people ask about scale up. Um, so tangential flow filtration, and so basically I have this book open and it's a pretty good book. So we're just gonna dive into it. So process development, filter sizing, design consideration, normal flow filtration, flow filtration, tangential flow filtration. In an interview, you can say you can give at least one example of filtration by watching this video. Uh, so we are also gonna go through modeling. Uh, so this is a example of normal filtration. As you know, there are two types of filtration: normal flow filtration and tangential flow filtration, which is also known as cross flow microfiltration. So this is normal filtration. As you can see, these are the lenticular filters. They are stacked up, and the pressure is applied, and the filtration has happened. This is a um, single-use filter cartridge with integrated aseptic connector. This is for single-use systems. Nowadays, mostly people are using single-use installation for the normal flow filters in stainless steel housing. Cord 0, cord 7. Common parallel design include 3 by 30, 5 by 30 inches. Uh, After installation, the housing base plate, the housing dome, is set in place and sealed with a gasket and a clamp. Inlet and outlet connections are made using triclover fitting. So these are the tests that are done prior to filter use. Pressure hold test. So basically, this is the most basic one, and it tests for no major leaks in the system. So you pressurize the upstream side of the filter at low pressure and then measure pressure decay, and then you can verify the system is intact or not. Bubble point, it is done when the filter is fully wet, and then you pressurize this wet filter with air, and then slowly increase the pressure until the force on the upstream side of the filter exceeds the surface tension of the water in the filter's largest pore. And then when this pressure is achieved, when you hit this pressure, then you know this is essentially your bubble point pressure, and then the filter resulting in bulk airflow. So the minimum pressure at which bulk airflow begins is called the bubble point. You can just ignore the diffusion for now, it's too much information. Conditioning is done on a case by case basis. So when you do your tech transfer, the decision should be made around that time, and then the mode of operation. So this is pretty important. So you have constant application, the feed vessel is overlaid with air. In constant pressure application, the feed vessel is overlaid with air or nitrogen. So for example, in constant pressure, you have the vessel where the feed is, I would say, where you're supplying the feed from. In that vessel should have air or nitrogen as an overlaid, and then the liquid is forced through the filter. And filter fouling manifests itself as a decay of filtrate flow rate, and therefore it can be important to measure either flow rate or filtrate volume in order to ensure that the filter is operating correctly. So you gotta measure the either the flow rate, filtrate volume, this, or either the flow rate in constant pressure application are common in cell culture media prep and buffer prep operations. So the constant pressure operation is mainly for buffer prep, and then cell media prep is not really the integral part of your downstream processing, I would say. For example, you have a UFDF and depth filtration. For those applications, I think you are better off using constant flow, are common when linked to chromatography steps or depth filtration, as these operations are typically already performed under constant flow, and the normal flow filtration can therefore be integrated in line, reducing the overall process complexity of the process. Disposal, as mentioned previously, normal flow filters are almost exclusively used one time, and therefore clean in place operations are uncommon. Uh, In order to ensure high filtrate yield, compressed air can be applied to the upstream side of the filter in order to displace as much filtrate as possible. Buffer flushing can also be employed to maximize step yield, so that's another good point. After this is complete, filter housing are depressurized, opened, and the filter is removed from the housing and discarded as biohazard. Filter housing are generally cleaned in place or cleaned out of place using sodium hydroxide. Process development. So I was mentioning earlier, this is the question that is asked a lot during an interview. So you can say that the normal flow filters are highly scalable, and such common scale models have been in existence for many years to accurately predict the performance of filters at scale using minimal product samples at the product process development bench. So you can say something along the lines normal flow filters are highly scalable, so you have done some small scale studies as a process development. But the major issue to watch out for in a scale down process development is the smaller scale test results are more prone to increased variability due to filter heterogeneity, and therefore safety factors should be employed. So this is the variation, increased variability due to filter heterogeneity. Heterogeneity. Multiple tests should be performed when scaling up in order to account for potential variation that can be magnified at a small scale, and in some cases it can also be useful to apply correction factors to account for the differences in device design. Small scale filtration studies are usually performed on flat membrane sheet, while large scale devices are built using pleated filters. That's true. So pleated filter are look like this. These construction differences can result in shifts in filter performance, but these shifts can be understood and accounted for in a scale-up calculation. So you have to, when you're giving an interview, somebody asks, uh, if you're giving an interview, let me write this down. So basically, you need to say that, otherwise, you're not gonna get a job. So in some cases, it can be useful to apply correction factors to account for the uh, device in differences in device design. Small-scale filtration studies are usually performed on flat membrane sheet, while large-scale are built using pleated filters. These construction differences can result in shift in filter performance, but these shifts can be understood and accounted for in scale-up calculations. So you need to say that somehow. You can say that I use flat membrane sheet in my scale-up studies. So there are some differences in devices in a scale-up device, because the scale-up devices are built with pleated filters. So these construction differences can result in shifts in filter performance. So these shifts can be understood and accounted for, and you can say you applied safety factors as well. As in the case with operation at scale, filtration development is primarily. So this paragraph talks about basically constant pressure and constant flow. So which one is easier? As you know, constant flow is used for chromatography and UFDF. So easy to implement, provides more accurate estimates of filter requirement for constant flow processes, provides reliable screening, uh, requires larger fluid volume and longer test times. Endpoints are not extrapolated. Filter sizing processes typically run under constant flow, clarification using depth filtration, serial filtration operation. These are the disadvantages. Sterile, constant pressure is basically, so basically clarification using depth filter and serial filtration operations. This is where you use constant flow, and then for constant pressure you use median buffer filtration and sterile filtration and various filtration unit operation, virus filtration, and membrane-based pre-filter unit operation. So it's really important. So all the virus, you when you go to a, let's say, map process, you do have virus filtration, and so you can say they say viral inactivation. So you get constant pressure was used basically, and depth filtration for clarification they use constant flow. So you only need 350 ml for 25 millimeter disc, and what is this? 1 liter for 47 millimeter disc. So that's a pretty small scale for constant pressure. Although there are many textbooks and reviews, blah blah blah. Constant pressure filter sizing. The technique involves the addition of samples to a pressuri- pressurizable vessel with the filter attached to the vessel outlet. Equipped with an on and off valve, a gas overlay is then used to pressurize the vessel to a specified pressure, and the inlet valve to the filter is open, at which point the change in filtrate volume is monitored as a function of time. The filter follows the rate of volume change. The filtrate flow rate decreases. The experiment is continued until a sufficient flow rate decay has been achieved. A typical recommendation is to run the experiments until at least 75% of the initial flow rate is achieved. By plotting the experimental data obtained in the form of time volume versus time on x and y plot, and using linear regression to estimate the slope and y-intercept of the resulting line, two filtration parameters can be estimated: the maximum capacity of the filter and the initial filter flow rate. The maximum filter capacity represents the volume of filtrate process when the filter is completely blocked and the filtrate flow rate drops to zero. These parameters that can be used to determine the minimum required filter area for a given operation using this equation. So basically, by plotting the experimental data obtained in the form of time volume versus time on x and y, plot and using linear regression to estimate the slope and y-intercept of the resulting line, two filtration parameters can be estimated. So you gotta plot the time over volume versus time. Okay, yeah, so the initial filter flow rate will show up. That's true. Yeah, it makes sense. So this is how you. It's pretty important actually to plot this, and then in an interview when they ask you, you can say you can find the maximum flow rate, maximum capacity of the filter, 1 over slope, and the initial filter flow rate. The maximum filter capacity represents the volume of filter process when the filter is completely blocked and the filter flow rate drops to zero. And then you use this equation. Let me magnify this. So you can use this to calculate your area for a given operation. So you have area, VB is your batch volume to be filtered, and TB is the time required. 1 over J, or 1 over intercept. 1 over J is your gonna, this is your intercept, initial flow rate, and 1 over this is your slope, the maximum capacity. That's true. Constant flow filter sizing. This technique involves the addition of samples to a vessel that is connected to a pump capable of producing a constant flow rate. Example, peristaltic pump. A filter is connected to the discharge side of the pump and a pressure gauge is placed upstream of the filter. I'm getting tired, man. Filter is connected to the discharge side of the pump and a pressure gauge is placed upstream of the filter. Filtrate is collected in a second vessel and pressure and filtrate volume are measured as a function of time. As the filter falls, the pressure upstream of the filter increases. That's true. Commonly, constant flow experiments also include a measurement of filtrate quality. The experiment continues until the pressure upstream of filter reaches a predetermined target or the filtrate quality becomes unacceptable. The moment at which these particular particulates appear in the filtrate is referred to as breakthrough, a term borrowed from chromatography operation. Data from constant flow experiment is plotted in the form of pressure over flux as a function of filter load, volume over filtration area, and an empirical model based on a second or third order polynomial is fitted to the data. This model is then used to calculate the required filter area for a given batch volume, process time, and maximum pressure drop using the following iterative techniques. Gas and initial volume of for area. Calculate the flux for the given value, calculate final loading, calculate resistance, calculate pressure drop, compare calculated pressure drop to given target. Alternatively, a mechanistic model such as standard pore blocking model can be used for filter sizing. Mathematical modeling can and should be used for development and optimization of filtration operations. This section focuses on the simplest and most commonly used filtration model. Equipment based parasitic losses in pressure can result in apparent nonlinearity when scaling. Therefore, the filter housing type and size and process flow rate must be considered when scaling up. So we have to go through this again. Oh my goodness, this is crazy. Yield and recovery. So basically, you applied safety factor to an area based on this, so it's not that difficult. It is rare that normal flow filtration operations are implicated in product yield investigation. That is to say that yield on normal flow filtration step approach 100% in the majority of well-designed processes. In the process development workflow, high yield is ensured by verifying that the chosen filter medium is compatible with the filtered species and there is minimal non-specific binding that could negatively affect yield. This is generally uncommon for modern filtration media to present compatibility problem with a typical component in buffer, cell culture media, and or product intermediate stream. In a manufacturing workflow, high yield is ensured by implementing steps to displace filtrate from the filter prior to dismantling and disposal. These steps can include the use of air to displace the remaining liquid on the upstream and or downstream. Productivity. High productivity of normal flow filtration operations based on good process development. It is important to match the pore size of the filter to the particle size of the contaminant species in order to ensure a good usage. Wow. Red 30. I think 30, 40. Ah, follow that. This is cross filtration. Oh my goodness. Oh my goodness. This is for another video.